Hi everyone. So continuing our class number 1 for the pendulum experiment, today what I want to talk to you about is the measurement circuit for measuring the period of a pendulum. Now I know you're not going to have the opportunity to build this circuit for yourselves, but it's really just a pretty small modification to the timers you've already built. So let me talk about what it is and how it works. So once again, right, experimentally we're trying to measure the period of a pendulum, right, as it swings, right? So let's think about what happens, right? So if I let this go, it's going to swing through the bottom here. It's going to come up. It's going to reach that turning point. It's going to come back. Now this is not yet one full period, right? Because we need a period means going through one complete cycle. So it comes back up here, and that would be one complete cycle measured from if I released it up here. Now what we're going to do in our experiment is we're going to actually be sensing what happens when the pendulum blocks light through our photogate as it hangs down sort of near the bottom of its swing. So that's a little tricky, right? Because at the ends we can just watch it hitting the ends, but swinging through the bottom we have to be careful. So let's just sort of draw a picture and turn that into a timing diagram, and we'll see what we get. Okay, so I'll just draw the position of the pendulum at a couple of time points and indicate the direction it's moving. So let's imagine we let it go and it's swinging down this way. Then it's going to, at some point, be hanging straight down and swinging to the right. Then going up, it'll turn around and come back like this, swing back down through the bottom here, and then go this way, swing back down. Oops. And finally hang straight down again. Let me just move that. I'm running out of board space. Now, if we set up our photogate so that it detects when the pendulum is blocking light right near the bottom, so like imagine my finger here is my photogate, then we've got to be careful, right? So let's assume that, let's draw the signal from our photogate, so coming out of the Schmidt's trigger inverter, so that the signal is high when the light is blocked. Now if we set up that photogate right, it's not going to be blocked over here because the photogate is shining right down at the middle. So I'll write from PG from photogate. So nothing here. Now here, right, swinging through the middle, we have a block. So I'll draw it'll be high for a short interval while it's blocked. Nothing, 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 until we're back at the center, right? And then we get another block, something like that. Again, nothing, 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 until we get, whoops, a block over here. Now, what we want to measure, right, is one period, and that's going to be one complete cycle of the motion. So that's actually here. One. Right. The circuit that we use for the linearly accelerated motion experiment, right, measured the length of a single block. Now we want to do the time between sort of these two blocks that aren't adjacent. Well, you thought about how you might be able to do that on one of the homework assignments. And the key turns out to be using a divide by 2 circuit. So let's imagine if we had if we took this signal and sent it through a divide by two or toggle circuit, so toggle, I'll call that divide by 2A. Okay. So we assume that we cleared our divide by 2, right? And so at this first rising edge, the signal goes high, right? Nothing, 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 until we get another rising edge. Now this drops low, and then no change again until we get another rising edge there. Now, this isn't entirely what we want either, right? Because we want to measure, our timers are, with our AND gate, are set up to measure the length of a high signal. And this is half a period, not a full period here. Well, the answer to that is to simply send this signal through another divide by 2. So again, if we assume that we clear it at the beginning, what that will give us is nothing here, rising edge here, goes high, no change at all until this rising edge. And that is exactly what we want. This signal has a length equal to 1 period of our pendulum. So if we AND this signal with our clock, we can then feed that to our counter and be able to measure the period. Let me take a minute to erase this, and then I'll draw the important part of the circuit, and then we'll go and look at the diagram, and the complete diagram in your lab manual. Okay, so here's what we're going to do. So we're going to have that signal from our photogate from G, so it's blocked. And we're going to feed this into a pair of cascaded divide by 2s. So I'll draw a flip-flop here. Here's my clock, here's my D, my Q, and my Q star. A bubble over here. So it's the classic flip-flop waits its tail. So I'll draw that connection thusly. Then we'll take this flip-flop and use it to clock the second one. So I'll draw, maybe I'll use, I'll continue here. Again, have this bite its tail. And then now the signal from here can go and feed our AND gate with our clock, which is our square wave as we've been using. And now this can get fed to our counters. All right, everyone. So here's the diagram of the circuit in your lab manual. So a few things to point out. It's just like we talked about. Maybe let's first focus on the parts that are the same. We still have our signal generator here, right? And we have the output of whatever coming from the phototransistor after some stuff. That's still being combined with an AND gate, and that's feeding to count up of our cascaded binary counters just like we've had before, we still have a push button to clear the counters, just as we had for the lamb experiment. So where things get a little bit interesting is, as I described with the circuit before here. So here's our photogate, our LED as usual, our photo transistor, and our Schmidt trigger inverter, so that's signal C over here. So just like I drew on the board, we take this signal, feed it into one divide by two circuit with a flip-flop, so biting its tail. We take the output of that and use that to clock a second flip-flop, divide by two, and then it is this signal that goes to the AND gate. Now, the one other piece here is the switch here, which is tied to clear star of the clear inputs, the active low clear inputs of both flip-flops. So remember that the bubbles mean that for an active low signal, right, if the switch is set that the input A here is low, then these flip-flops will always have an output Q of 0, so they're or low, so they're not going to do the dividing by 2. It's only when we don't assert clear by having the switch high that the two flip-flops will do what we want them to do, as we talked about on the board. So it's this circuit, right, gives rise to the timing diagram we talked about up here for measuring the period of a pendulum. Okay, so at this point we've talked about the theory behind the period of a pendulum at small angles, and we've also looked at the measurement circuit. So I'll be posting some videos later that where I filmed part A of the lab. And this, remember, involves checking that small angle theory, right? Checking the period of a pendulum as a function of its length. So I'll show you the circuit that I built, and I'll walk you through some of the measurements. And I know this is not the same as you actually doing the experiment, but you'll see how it could be done, and I think you'll enjoy analyzing the data.